Now, um, one important application of infinite sequences, okay, is the representation of is in representing infinite summations. Okay, so informally, if an is an infinite sequence, then the sum of its terms. Okay, remember that a1, a2, a3 up to an. Okay, are the terms of the sequence an. Okay, so if we take that sum, which is its shorthand notation is this summation notation. Okay, we call this now as an infinite series or simply a series. Okay, the numbers a1, a2, a3 up to an are the terms of the series. For some series, it is convenient to begin the index at 0, okay, or some other integer. Okay, for us, our index starts at 1. Okay, so we would like to reserve some flexibility here. Okay, so either we start our series at 0, we started at 1, or in a less common fashion, we will start them at an integer other than 0 or 1. Okay, but either it's 0 or 1. Okay, so and in that case, okay, you need to be very you need to look carefully, okay, at where your sequence starts. Okay, because that plays a role. That greatly plays a role on how your sequence would actually behave. Okay, so as a typesetting convention, it is common to represent an infinite series simply as this one. Okay, if and in that case, if we're representing your sequences as that one, the starting value of the index must be taken care from the context of the statement. So must be taken from the context of the statement. So which means that if we don't write the indices, okay, we don't write the limits n equals 1, sorry, n equals 1 up to infinity, okay, we assume that you know it from the context of where the statement was coming from. Okay, now the main task in in the lesson of infinite series is to find the sum, okay, of an infinite series, and we begin by finding what we call partial sums. Okay, so the partial sums of your series is basically the sum of the first terms of the sum of the sum of sum of the terms, the sum of some terms. Okay, so that I'll be making it clear. Okay, so for example, the first partial sum is simply the first term. The second partial sum is the sum of the first two terms. The third partial sum is the sum of the first three terms. Okay, and so on. And so the nth partial sum, we call this as the nth partial sum, is as the sum of the n terms. Okay. Now from there, we will be able to write a sequence of partial sums: S1, S2, S3, S4, up to Sn. Okay. So we will be able to create a sequence. Okay. We will be able to create a sequence of partial sums. Now this is a very important definition of this sequence, because this is where we anchor our definition of the convergence of the sequence. Because if this sequence, okay, the sequence of the partial sums converges, the series is said to converge, okay, and has the sum indicated in the following definition. Okay, so for the infinite series, the sum of an, okay, the nth partial sum is given by this, okay, as discussed earlier. Okay, if the sequence of partial sums, ito, converges to S, okay, it means that this sequence converges to some number S, okay, then the series converges, okay, and S is the sum of the series. So if you remember from the previous lesson, that for us to be able to determine if this sequence, okay, is convergent, we would have to look for the limit of Sn as n approaches infinity, which may be some number, say S. We used L in the previous lesson. Okay, so if this S is a finite number, okay, if this S is a finite number, okay, then number one, your series an is convergent. Okay, and number two, the sum of an is actually S. Okay, now if this sequence is divergent, then the series diverges. Okay, so that's how we define a convergent and divergent series. And also, that's fundamentally how we find the sum of that series. Okay, so say for example here, the series 1 half plus 1 4 plus 1 8 plus 1 over 16 has the following partial sums. Okay, so we have the first partial sum as simply 1 half, the first term. Okay, the second partial sum is the sum of the first two terms, 1 half plus 1 fourth, which gives you 3 fourths. Okay, the sum of the first three terms, 1 half plus 1 fourth plus 1 8 is 7 over 8. Okay, and so on. Okay, now you can write the sequence 1 half, okay, 3 fourths, and 7 eighths. Okay, let's look at for the fourth term just to be sure. The fourth partial sum is 1 half plus 1 fourth plus 1 8 plus 1 over 16. So the LCD of this is 16. So this is 8 plus 4 plus 2 plus 1. So this is 12, 14, 15. So this is 15 over 16. Okay, and so on. Now, again, from the previous lesson, for us to be able to find the convergence of this series, okay, of this sequence, I mean, okay, we need to find its nth term. Okay, so we see that the denominator is obviously powers of 2, 2, 4, 8, 16. Okay, so that the denominator of that is 2 raised to n. And as you can see, the numerator is, aside from them being odd numbers, but this is not a sequence of odd numbers, because the sequence of odd numbers is 1, 3, 5, 7, 9, and obviously there are some terms missing. But if you observe closely, the numerator is 1 less than the denominator. For example, this is 1 is 1 less than 2. Okay, 3 is 1 less than 4. 7 is 1 less than 8. Okay, and 15 is 1 less than 16. Okay, so that the numerator is actually 2 raised to n minus 1. It's actually 16 minus 1. 16 is 2 raised to n, and then subtract 1 to 8. So you have 15, and so on with the other terms. So you'll have this as the nth term. Okay, so this is now the nth partial sum. Okay, and this is the sequence of your partial sums. So that's your S n. Okay, now what we need to do here is to find number one, whether the sequence of sums actually is convergent. Okay, it is actually convergent. So we find its limit, the limit of 2 raised to n minus 1 over 2 raised to n. As your n approaches infinity, okay, I can actually divide the numerator and the denominator by 2 raised to n. Okay, so I can have it as 1 over 2 raised to n over 1 as n approaches infinity. And as you can see, if I did evaluate this limit, this becomes 0. Okay, so the limit is actually 1 over 1 or 1. Okay, so what can we expect from this results? Okay, number one, since your partial sum or the sequence of your partial sum is convergent, it follows that the series sum of an is also convergent. Okay, since again it starts with the fact that your the sequence of your partial sum is convergent because it has a limit. Okay, so it follows that your series, the indicated series from which we obtain this the sequence of partial sum, is also convergent. Okay, and that the more important thing, that the sum of this series, okay, that is the sum of the sum of 1 over 2 raised to n as n for n equals 1 up to infinity, okay, is actually equal to 1. This is actually the sum of this series. Okay, so we can numerically verify that using Excel, okay, with this one. So this is your given sequence series. Okay, so the terms are 1 over 2 raised to n, where E3 is actually your n. Okay, now The first partial sum is given as the first term. Okay, that is what the assertion is here. Okay, the first partial sum is the first term. Okay, while the succeeding partial sums is obtained by adding this new term to the previous partial sum. Okay. We can think of finding the next partial sum as a recursive thing. Okay. We can think of it as a recursive thing. That is, we find the present sum, or the current partial sum in terms of the previous partial sums, because that actually simplifies the operation. Instead of actually going back, on writing up the previous terms, okay, like in this case, okay, you can actually say, for example, it is obvious that this 1/2 plus 1/4 is this 3/4. So instead of actually saying that this is 1/2 plus 1/4 plus 1/8, I can actually say that this is 3/4, the previous sum, okay, plus 1/8. Same thing with with the next Okay, instead of saying that this is 1/2 plus 1/4 plus 1/8, because that forces me to go back from the previous terms of the sequence. Okay, so instead of actually going back dun sa previous terms of my sequence, I can actually use the previous sum, which is basically, this is 1/2 plus 1/4 plus 1/8 is basically your S3. Okay, which is that 7/8. Okay, then I'll add it to 1/16. So this is my previous sum, this is my present term. So previous sum plus present term. This is what we did here. The previous sum, okay, the previous sum, this one, versus the present term. So that is our present sum. So we did that. We use that algorithm. Okay, we use that recursive way of finding the next terms of your partial sum sequence. So as you can see, your partial sum sequence, okay, is inching and inching closer towards 1. Okay, with sufficient number of terms. Okay, with sufficient number of terms. Let's say we add more terms here. Let's have it reach to up to 100 terms. Okay, so we copy these formulas. Okay, and see that eventually your sequence will actually reach, or your partial sum sequence will actually reach 1 as its limit. So that is the one that we are obtaining here. Okay, this is the one that we are obtaining in this operation. Okay, so that is also the sum of your series. Okay, so here, we have the partial sequence. Okay, I mean, we have here the partial the series 1/n minus 1/n plus 1. Okay, which is this one. Okay, so as you can see, with this, with the pattern, with how this sum, or how this sequence is expressed, you can see that this and this would get subtracted. Okay, they would cancel, these terms would actually cancel each other out, and they eventually become 0, as well as this one and this one. Okay, so for example, S1 is simply 1. Okay, minus 1/2. Okay, that's your S1. S2 is the previous sum, which is S1, plus the next term, which is 1/2. Okay, minus 1/3. And S1 is 1 minus 1/2 plus 1/2 minus 1/3. Okay, so what is the idea here? Okay, what's the big idea? Eventually, if you take a good look at this one, the partial sum would simply be the first term, this one, okay, minus the very last term of the series. Okay, the very last term of the series of your partial sum. Okay, so in this case, for example, in the case of the second partial sum, that's 1/3. Okay, in the case, for example, of S3, okay, that's S2 plus that's S2 plus the present term, which is 1/3 minus 1/4. Okay, and S2 is uh, this one. Okay, so that's 1/2, 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. So this cancel each other out. Ang naiiwan dyan is itong 1 at saka yung last term. Okay. The last term of the partial sum, which is 1/4. So basically, if you assign it to be n, if you assign the subscript of your partial sum to be n, that is basically 1 over n plus 1. So the partial sum is given always as 1 minus 1 over n plus 1. Okay. This kind of sequence, this kind of series is what we call a telescoping series. We use the term telescoping series here. Okay. Telescoping means parang you get to obtain the sum because the terms of the series in between are canceling each other out and tends to become 0. So what remains are the first and the last term. Okay. So yun yung telescoping. Later on, we will formally define what a telescoping series means. Okay. So this is the first and the last term of your series. So in which, if you actually find the limit of that becomes 1. So the limit of the partial sum, okay, the partial subsequence is 1. Okay, and therefore the sum of this infinite series is eventually 1. Okay. Later on, there is also a technique by which we can but as a telescoping series, we will be able to get this sum. Okay. Next, ito pala yung discussion ng telescoping series. So we'll formalize it later after I discuss letter C. Okay. So the series, the summation of 1 equals 1 plus 1 plus 1 plus 1. Okay. Because obviously, your Sn is basically n. Okay. For example, S1 is 1. S2 is 1 plus 1 or 2. S3 is 1 plus 1 plus 1 or 3 and so on. So therefore, Sn or S sub n is equal to n. And its limit, the limit of n as n approaches infinity is approaching infinity also. So therefore, since you don't have a limit, okay, your partial sum diverges, and therefore this series also diverges, and therefore you don't have a sum. Okay, so that's for letter C. Now, so again, the series featured in example 10b is called or this is not example 10b. This is simply example, example 10b pala. Is called a telescoping series of the form b1 minus b2 plus b2 minus b3. Again, a feature of the telescoping series is that middle terms tend to be cancelled each other out. Okay, so the sum of a telescoping series would exist if, number 1, the nth term or n plus 1 term would actually have a limit. It actually would converge. Okay, so if a telescoping series will converge if and only if Bn, okay, the sequence Bn is a convergent series. Okay, I mean sequence. Okay, so if the limit of Bn as n approaches infinity, okay, equals a certain number L. Okay, so if this sequence is convergent, then a telescoping series of this form, okay, would also be convergent, and its sum would become this one. Okay, in this case, like example B. Okay, Bn here is 1 over n. Okay, Bn is 1 over n. Okay, we know from the first lesson, okay, from lesson 4.1, that the limit of 1 over n as n approaches 0, okay, is as n approaches infinity, okay, equals 0, okay, because this is a decreasing, okay, and that so since your Bn, okay, is convergent, okay, we will have a sum, and that sum, okay, equals, okay, the sum of that telescoping sequence is given as B1, the first term, okay, which is in this case 1 over 1. So that is 1. Minus the limit of bn plus 1 as n approaches infinity. So in that case, that becomes the limit of 1 over n plus 1. Okay, again, your bn is 1 over n. So bn plus 1 is 1 over n plus 1. So the limit of 1 over n plus 1 as n approaches infinity is basically 0 also. Okay? So therefore, the sum of this is equal to 1. Yun yung nakuha natin doon sa example natin kanina. Okay, example 11. Find the sum of the series 2 over 4n squared minus 1. Okay? So how do we write this one? Attack this one. This example actually showed that it would be possible that to turn this into a telescoping series. Okay. What the example did was to turn this into a telescoping series by writing this as a sum of in terms of its partial fraction expansion. Okay. So if you actually factor 2n plus 1 and 2n minus 1 there, okay, and let's have a over 2n plus 1 plus b over 2n minus 1, okay, where a is 2 over 2n minus 1 if n equals negative 1 half. So that should give us 2 over negative 1 minus 1. So that's negative 2. So that's negative 1. Okay. Kaya negative 1 yung coefficient nito. While b is computed as 2 over 2n plus 1 with n equals 1 half. Okay. I'm using the cover-up method here. Okay. This is equal to 1 half. So 1 plus 1 to 2 over 2. That's 1. So, kaya 1 ito. Okay. So if you actually write out the terms here, the terms of this sequence, you would actually have this one. Okay. Which obviously is it turns out to be a telescoping series. Okay. It turns out to be a telescoping series. So this is 1/3 plus 1/3. So they cancel each other. Negative 1 here gets to be cancelled out by the next term. So you'll have that one. Okay, so there. Okay. So to be able to find the sum of this, this is simply finding v1, okay, from here, okay, which is basically here also. So that's 2 over 4 minus let's just simply find it from here. Okay, so this is 1 over 2 minus 1. Okay, so that's 1. And then this is the next term. Okay, so you'll have the limit of that bn plus 1 is the limit of 1 over 2n plus 1 as n approaches infinity, which is 0. Okay, which is essentially 0. Okay, so therefore the sum of this is 1. There. So if you have a chance of writing the partial sum in terms of a telescoping series, okay, a method here as presented by example 11, okay, can actually be used to find the sum of that kind of series. But as you can see, this only applies to certain class of series, okay, to certain class of expressions, okay. So like this one, okay, which the special case here is that this is factorable into sum and difference of terms, okay, and that the numerator are actually equal to each other and that they have different signs. So those are the special cases that were involved in example 11. So not all sequences are or do have special forms such as that one. Okay. So but if you can recognize them, that actually simplifies your solution. Okay. Now we proceed with geometric series. Okay, in which is should be familiar with everyone already, because you may have studied this before, okay, in your high school days, and even in your introductory mathematics in college. Okay, so a geometric series is a series, okay, um, having a in which the terms are actually generated by multiplying a constant number. That number is the common ratio r. Okay, so to get ar, you need to multiply r to a, and to get ar square, you need to multiply r to ar. To get the next term here, you need to multiply r here. Okay, so that's a geometric series. Okay, and take note, our geometric series, as per definition, has a lower limit or starts at n equals 0. Okay, so that's one thing that you have to be cognizant of. Okay, so here we say that r here is the common ratio. Okay, now by theorem 6, your geometric series would converge. Okay, if the absolute value of r is between 0 and 1. Okay, that is, if r is negative, if r is negative, it should be between -1 and 0, while it is between 0 and 1 if it is positive. Okay, the thing is that r should be a ratio, whether it's negative or not positive. It should be a fractional value, so that your geometric series would converge, your infinite geometric series would converge. And should these conditions be satisfied, okay, this is the sum of your geometric series. Okay, so let's look at example 12. So here we have 3 times 3 over 2 raised to n, which is rewritten as 3 times 1/2 raised to n. If you expand that, that becomes 3 times 1, okay, plus 3 times 1/2 plus 3 times 1/2 square, and so on. As you can see, this is a geometric series because, number 1, to be able to generate this term, you need to multiply a constant number here, which is 1/2. Same thing with this one. To be able to get this term, you need to multiply a constant number here, which is 1/2 also. So that becomes that makes 1/2 your common ratio. Now, since r, your common ratio, is between 0 and 1, it's a fractional number. Okay, so therefore, by theorem 6, this geometric series would converge. Okay, and where it would converge. Okay, so the sum of your 3 over 2 raised to n for n equals 0 up to infinity is a over 1 minus r, where a here is 3. Okay, the constant number 3. So we have 3 over 1 minus 1/2. So that should give you 6 as its sum. Okay, now you may be able to verify this. You may be able to verify this by numerically computing the partial sums and see that the sum is actually approaching 6. Okay, Excel is a good tool for that. Okay, you can also use MATLAB, because at this point you should be able to learn how to write scripts that can generate sequences of numbers. Okay, so there. Here, in this case, this series expands to 3 halves raised to 0 plus 3 halves raised to 1 plus 3 halves raised to 2, and so on. So this is a geometric series. Okay, clearly this is a geometric series. Again, for you to be able to get this, you need to multiply a number from here. Okay, so, and that number is 3 halves. Okay, same thing with this one. To get 3 halves square, you need to multiply 3 halves to 3 halves. Okay, and so on. So the common ratio here is clearly 3 halves. But this 3 halves is actually greater than 1. This is not a fractional number. It's actually a number, okay, that is greater than 1. Okay, and according to theorem 6, this is a divergent this is a divergent geometric series. Okay, because yun, because your common ratio r is greater than 1, so therefore the series diverges. Okay, so the convergence of a series is not affected by removal of a finite number of terms from the beginning of the series. Take note, the convergence, okay, not the sum. Okay, if you're trying to take a look at at the convergence of a series, okay, we may be able to get a better view of the convergence of the series by considering some parts of your series. Okay, some parts of your series, because the first few terms might actually lead us to suspect that series is a divergent series. But if you actually remove some of those terms and just consider some of the few, okay, we may be able to get a convergent series. Okay, and then just add some of this of the first few terms that you have removed initially, and then add it to then you have still a convergent series. Okay, so the convergence of a series is not affected by removal of a finite number of terms from the beginning of the series. For instance, the geometric series, okay, this geometric series, okay, both converge. Okay, whether you begin at 0 or you're 4, both of them will converge. Okay. Now this, because the sum of the second series is 2. Okay, the sum of this is 2. Okay, you can conclude that the sum of the first series can be done by removing the first 4 terms. Yung 1/2 raised to 0, 1/2 raised to 1, 1/2 raised to 2, and 1/2 raised to 3. First 4 terms. By removing these terms from the sum of this, you'll be able to get the sum of the series. That's what I'm telling you earlier. If you have a series that is convergent only on, say, n equal to 4, okay, and from n equals 0 up to n equals 3, your geometric series seems not to converge. Okay, because there's parang ganito. Let's have, say, 3 halves raised to 0 times 1/2 raised to 0 plus 3 halves raised to 1 plus times 1/2 raised to 1 plus 1/2 square plus 1/2 cube, okay, plus 1/2 raised to 4, and so on. Okay, so this might look like a geometric series to you, okay, but technically this is not a geometric series. Okay, but if you actually remove these terms, these first 2 terms, okay, and just consider this, just consider those terms, okay, from n equals 2 up to this is a geometric series. This is a geometric series. Although the first 2 terms are not the terms of a geometric series, the next terms are actually are terms of geometric series. So you may be able, you can treat this to be a geometric series as the sum of 1/2 raised to n for n equals 2 up to infinity. Okay, so you can consider that as geometric series, which you can find now its sum. Okay, since this begins at 2, okay, since this begins at 2, you can start at the sum of your 1/2 raised to n for n equals 0 up to infinity, but remove the 2 terms, yung 1/2 raised to 0 tsaka yung 1/2 raised to 1. The sum of this is 2 minus 1 minus 1/2, so the sum of this is 1/2. So the entire sum of this is 1/2. Okay, and then you add these first 2 terms, so you add 3 halves there, you add 1 there. Okay, you add 1 there for 3 halves raised to 0 times 1/2 raised to 0 plus this one, which is 3/4. and that will be the sum of the sequence. Okay, so that is possible. Okay, so again, this series is convergent. Okay, this series is convergent. You may not be able to apply the entire geometric series in all of this. Okay, but still, as sinasabi natin, the convergence of the series is not affected by removal of a finite number of terms from the beginning of the series. So since we remove this, okay, it won't be, or it will not say that this is a divergent series now by removing this. Okay, or by including this series, okay, would make actually the entire series divergent. Okay, so there. Now these are the properties of your infinite series. So if we have a series multiplied by a scaling factor, okay, we can simply multiply the sum of that series to the scaling factor. The sum of two series, okay, is equal to their sum, okay, and the difference is equal to their difference. Okay, so there. Now, here's what the common task that we need to determine. So again, one thing that we need to understand about our series is that we need to find whether that series converges. Okay, so the first question is the series convergent. Okay, number two, okay, if it is convergent, what is its sum? So actually, later on there would be a third question to that, is that and if it can be answered by the first two questions, okay, but basically one thing that we also have to realize later on is that we need to be able to make sure that your series actually converges to the sum, because there especially in the topic later on, that it would be a question whether yes, there is a sum, your series is convergent, we are able to get the sum, but the question is your series converging to that sum? Okay, in these cases we will not be able to we will not consider that question, but later on in later topics, especially when we're dealing with functions expressed as series, okay, this will be one of the questions that we need to answer. Okay, so the determination of your of the convergence of your sequence actually involves many, or can be done in many ways. Okay, it actually depends on the form of the series. So that is what we will deal with from this lesson up to some time later. Okay, so we start with this test. Okay, we call this the nth term test for divergence. So the following theorem states that if a series converges, the limit of its nth term must be 0. Okay, so here, if your series is convergent, okay, then the sequence, okay, the sequence an is actually a sequence that eventually becomes, or the nth term of your sequence actually becomes 0. Okay, so that's theorem A. But this is not this is not really the essence of what we are trying to determine here. It's contrapositive. Okay, the contrapositive of theorem 8, it's converse. Okay, is what will be used to test whether a series is divergent. Okay, so that's why this topic is called test for divergence. Okay, so it actually determines that if it actually says that if the limit of an as n approaches infinity is not equal to 0, okay, then the series must diverge. Okay, then the series must diverge. That's theorem 9. Okay, so if the limit of your nth term for your series is not 0 as n approaches infinity, then the series, this given series is divergent. Okay, again, if the limit of if the series is convergent, okay, if the series is convergent, then it is more or less that the limit of the nth term as n approaches infinity is 0. That's theorem 8. Okay, but what we would want to know is whether a series is convergent or divergent. Here kasi, we have the knowledge of your series being convergent. Okay. So let's obtain its contrapositive, which is theorem 9. Okay. And that contrapositive now is now useful to us to determine whether a series is divergent. Okay, is divergent. Okay. The requirement for a series to diverge is that this limit should not be equal to 0. It turns out to be 0. Okay. If it turns out to be 0, pag nag-test kayo, tapos it turns out that becomes 0, don't conclude that the series is convergent. It doesn't follow that. It doesn't work on that. It doesn't work that way. Okay. All we know is that if it is not equal to 0, the series automatically will diverge. Okay. But if it is equal to 0, then no. We don't have any conclusion about that. Okay. So here, let's take a look at example 13a, okay, in which we try to take a look if the limit of 2 raised to n, the nth term of your series, as n approaches infinity, okay, is equal to 0, okay, which is clearly not, okay, because this 2 raised to n is increasing, so therefore its nth term would not be 0, but rather a very large number. So therefore, by theorem 9, okay, by theorem 9, okay, the series diverges. Okay. Here, okay. We take the limit, okay, we take the limit of n factorial over 2n factorial. Again, this is 2n factorial plus 1, okay, as n approaches 0. I mean infinity. Okay. Now, since both the numerator and the denominator becomes factorial, okay, it is easy to conclude. Okay, it is easy to conclude that the limit of 1 over n factorial as n approaches infinity is 0. Okay, so in that case, we can simply divide the numerator and the denominator by n factorial, so that this becomes the limit of 1, okay, over 2 plus 1 over n factorial. Again, I divided both the numerator and the denominator by n factorial, okay, and then evaluating this limit, this becomes 1/2. Now, the limit is not equal to 0, okay, so the limit of an as n approaches infinity is again not equal to 0. Here, it's 1/2. So according to theorem 9, so by theorem 9, this series is divergent. Okay. So according to theorem 9, this series is divergent. Okay. Now let's follow. Okay. For letter C, okay. Let's proceed. So for letter C, the n term here is 1 over n. So we evaluate the limit of the n term as n approaches 0, which is the limit of 1 over n as n approaches infinity. N, here n approaches infinity. So the limit of 1 over n as n approaches infinity is again 0. Okay, we have determined this parang 3 times na yata up to this point. So this is the 4th time. Okay. Now, since the limit is 0, this does not satisfy theorem 9. Okay, this does not satisfy theorem 9. Okay, so according to theorem 9, wala tayong conclusion. We cannot conclude that the series is divergent. Okay, according to theorem 9. Okay, but can we actually use theorem 8 to conclude that the series is convergent? Okay, the question is, can we use the theorem 8, okay, to conclude that the series is actually convergent? No. Okay, the answer for that is no. We cannot choose theorem 8, okay, to say that the series is convergent if theorem 8 says that if the series is convergent, then the limit of an must be 0. It doesn't say that if the limit of an must be 0, the series is convergent. No, wala siyang ganun sinabi. what theorem 8 said that if the series is convergent. Okay. Here, ang meron tayong information is that the limit of the n term is 0. Okay. Which is not which fails according to theorem 9, and it has nothing to do with theorem 8. Okay, it has nothing to do with theorem 8. So at this point we don't have any idea. Okay, we don't have any idea of whether this series is convergent or divergent. Okay, but this is a very surprising result to you. This might be a surprising result to you, that if you actually take the partial sum of that series, it actually becomes this way. And as you can see, it's actually increasing. Okay, that series is actually increasing. Okay. Now, you can argue that it's monotonic. Yes. That sequence Sn is monotonic. Monotonic. Okay. But the thing is that this is not bounded. It doesn't have an upper bound. Okay. It might not be obvious, but it actually is increasing continuously. Okay. So this is not there's no upper bound here. Okay. So again, from the argument that this is monotonic but unbounded, you cannot say that this series or that this sequence is divergent. Again, we don't conclude it that way. Again, the theorem on the bounded and monotonic sequence is that both of them, a sequence should be bounded and monotonic for it to be convergent. Okay, but since this sequence of partial sum is monotonic but unbounded, we don't have any conclusions about this one. But here's the thing: later on, we will be able to find out that this series is actually divergent. Okay, this series is actually divergent. Okay, so which may contradict with how you understand theorem 8 is. Okay, so not all sequences. Here's the thing. Here's a moral lesson about theorem 8. Theorem 8 just suppose that if your series is convergent, convergent. Okay, convergent. It follows that its n term is 0. Okay, and not the other way around. So this is okay, but this one is not guaranteed by theorem 8. That is, if this is 0, it is convergent. No, that is not theorem 8 is all about. Okay, so that is something that you have to understand about theorem 8. Okay, so that ends our so on in the next lessons we will be covering more tests. Okay, more tests of convergence for your series. Okay.